Hi, this is Dr. G. Welcome to our statistics review. This is a video that will cover some of the basics of statistics. Let's start with a few definitions. First, population. What is a population? Well, it's the entire collection of units of analysis or observations or elements upon which information is desired. It's just a large collection of individuals or objects known to have similar characteristics. So what are these objects, these elements? I referred to them a moment ago as units of analysis. Well, these are the units upon which measurements are taken. So populations are comprised of these elements or these units of analysis. Let's think of an example. How about the population of all college students or all graduate students? What are the units of analysis in this case? The unit of analysis, or the unit upon which measurements are taken, in this case, is students. So students comprise the population, and we're referring to all college students. We're interested in studying properties of some numerical characteristic of the population of units of analysis. So what's the characteristic that we might be interested in studying for all college students? Maybe grade point averages. So that's an example of a population, all grad students or all college students. The units of analysis are students, and the numerical characteristic that we're interested in studying in this case is grade point averages. So once we've identified a population of numerical values of interest, we take a sample. So there are different reasons why we take a sample. A couple of big ones. Number one is cost. In other words, it's a heck of a lot less expensive for me to take a random sample of all graduate students and measure some numeric characteristic like grade point average versus measuring that numeric characteristic for the entire population. So cost. And then the second reason is that it's possible to use sample information to obtain really good information that we can use to make inferences about the population. Basically, what I'm trying to say is sample information is high impact information. So if we take a random sample, or if the sample is truly representative of the population, I can measure some of the numeric characteristics of those samples and make inferences about the entire population. So I might be able to randomly sample 100 students versus the millions of students in the population, and I might be able to say something about those millions of students with my random sample. So that's the beauty of statistics and working with samples. Low cost, number one, and number two, high impact information. So once we get our sample, we often take an estimate of the following parameters. First, the mean. Next, the range. We can arrange grade point averages in ascending order to see what the lowest value is, to see what the highest value is. We can look at how grade point averages are distributed. So for example, we might expect to see a normal distribution for this particular variable. And we can measure the dispersion of the data looking at variance and standard deviation. We'll talk about all of these quantities in more detail in just a bit, but my point right now is simple. Instead of working with entire populations, we work with samples, and we can use samples to obtain measurements of important statistical quantities. Sometimes we look at the median and the mode and other measures of central tendency in addition to the mean. So for example, if the data is highly skewed or if kurtosis is high, we might prefer to look at the median instead of the average or the mean. And we can supplement that data with other numerical properties, for example, the interquartile range, the variance, and the standard deviation, just the ones that we've already mentioned. All right, so before we explore these concepts in a little bit more detail, I'm going to go ahead and go to my data, Actually, I'll go to the program that I'm going to run. I've got a projects folder under my C drive. So I've got a projects folder saved on my C drive. So if I click on my C drive and go to projects, there is a statistics review folder. And the program that I'm going to work from is stat review. There's also stats review. They're basically the same, but I'm going to work with stat review to recreate the stats review program. And this is what it looks like. So this isn't really a lesson on programming, but we often use statistical processing software packages to perform data analyses because it saves time. It can do some really fast, powerful things in programs versus using Microsoft Excel or worse, versus doing it by hand. So that's going to be something that we're going to do, even though it's not necessarily required for you to learn. So just pay attention to the basic statistical concepts, and I think you'll be in really good shape. But reproduce these programs to get some practice in Stata if you're working in Stata. And of course, you can also use Microsoft Excel. If you're taking one of my classes, then I'm probably asking you to reproduce these programs in Stata for credit. Okay, so I always start programs with the following lines of code: the version line, capture log, close, set log type text. That's to create a text file for logs. I create a log or a log file with this command, log using stat review, comma replace. If you want to learn more about a particular command, just type in help and then the name of that command. And this is the log file, or the help file for the log command. That's actually a little large, so I'll go to 12. So under the title, you'll see the manual that contains this particular command. You'll see the syntax, and you'll see all of the different ways that you can use this command. We're using log using the name of the file. The name of our log file is stat review, not stats review, it's stat review, because I'm working in my stat review.do file that I created. You can create a new do file just by clicking on this tab and writing away, or just going to File and Open. And you can start a new do file. It's really easy. So log using stat rev, the suffix for this file is a .log file, and then I'm inputting the replace option so that when I run this program more than once, it doesn't stop on an error. Hey, that file already exists. I'm going to replace that file every time that I run the program. So I can highlight the commands that I want to run, press this arrow, and if I go to view stat rev.log, I can see the log file. Of course, there's nothing in it because we haven't really done anything. Next, I set more off that so that Stata doesn't stop when the results window, which is here, is full. This is the results window. When it's full, Stata will stop. So I use this command, set more off, so that Stata flows smoothly through all of the results. This is a command to change directories. That just says go to a different folder, and the folder that I want my computer to work from is on the C drive under the projects folder, and it's the stats review folder. So if I run that, and if I type in directory into the command prompt, we can enter commands here. I can see all of the files that are in this folder. And again, if you're taking one of my data analytics oriented classes, you probably have a folder that contains all of these files. I'm going to import some data, but first let me just re-emphasize the point that I'm going to make. There are times when we use the median instead of the mean to learn more about the data under analysis. When do we do this? We do this when the data are highly skewed. So let me import this data. This is data that contains economic statistic information, income information. So if I click on Browse, you'll be able to see the data that we're working with. And we have real incomes for these different years, 1975, 1985, 1995, and 2005. And we've got tons of observations. We've got 100,000 data points. So for each one of these years, we took a random sample from the population, 100,000. I can obtain summary statistics for these variables by typing summarize. To do this in Excel would take forever. You'd have to highlight one column, input equals average if you want the average, and then highlight that data. Input equals STDEV for a sample, highlight. But instead, if I type in this command, it gives all of this information to me instantly. And if I want even more information, I can input summarize and then detail. And for every one of the variables, it'll give me lots of details in addition to the summary statistics. So you can tell by looking at the data that the skewness and kurtosis values for income, 1975, it's high. We'll talk about skewness later, but as you can see, these values are pretty high. We can visually inspect the data by looking at a histogram. So I'm going to put histogram. And again, this is just a graphical representation of the distribution of data. And I'm just going to pick one of these years and press go. Too many variables. Okay, that was an error. And as you can see by looking at this histogram, and you can create these types of tables in Excel too. Again, it takes forever and a day. But we've got a big hunk of information and then data that tails off to the right. In other words, it's very, very skewed. So let's look at 1975. The 85 data is so skewed, it's almost hard to even see. But here you can see that we have a right skewed distribution. When variables are normally distributed, they look like this. So we might look at income, or we'll put stock prices. I'll put stock prices. And this is the distribution. They might look normally distributed. But we just saw that income is very right skewed. It kind of looks like that, right skewed. The vertical axis is the density function. I'll just put f of x, or this is the f of stock prices, where stock prices are our independent variable. And if I want to get the probability of obtaining a particular stock price, I just go from the horizontal axis to the density function, out to the vertical axis, and then I'll get my likelihood or probability using the density function. There's actually a formula for f of x for normal distributions. That density function formula varies by distribution. Most of the variables that we're going to be looking at are normally distributed. We're going to be looking at sample statistics, which are almost nearly always normally distributed because of the central limit theorem and how sampling distributions work. We'll talk about that later. But again, this distribution just tells me, this would be the average stock price, how the data are dispersed around this average. And again, that sort of information can be very meaningful. Let's say we have two distributions. Let's say we've got stock A versus stock B, and this is the distribution of A. Of course, this is not drawn to scale. And let's say the expected return, or the average return for A, is equal to 15%. And let's say stock B has an expected return also equal to 15%. But let's say the data are distributed like this. In other words, they don't really spread out around the mean too much. So the range for stock B might be 12 to 18%, whereas the range for stock A might be negative 50 to, I don't know, 115% or something like that. So the point that I'm making is, if I know the measure of dispersion and the expected return, I can learn more about the data than just the expected return alone. So if I know standard deviation or variance in addition to the average, I can use that information to achieve a better understanding of the variable under analysis. Okay, so back to the example. We want to use the mean when the data are highly skewed. When the data are highly skewed, we should not use the mean. So if I go back to Stata, and if I look at the summarized information, the average is 38,000 a year to 40 to 40 to 48,000 a year. If you look at per capita income now, the average is probably about $57,000 per year. But if we lined up the entire population from the poorest to the wealthiest and looked at the 50th percentile, we would be able to see the income for which half of the people in the country make less and half of the people in the country make more. So let's solve for the median. I think we did this already, but you just input summarize in detail. And the median is the 50th percentile. So as you can see, in 1975, it's about $25,000, and this is inflation adjusted data changed to a particular year, so it takes into consideration changes in the cost of living. And from 75 to 85, it's the same, 25,619. 1995, about 24,000. And then again, back to 25 in 2005. So basically what we're saying is that for the middle income, middle class individuals, the median has stayed about the same, even though the average has increased over time. And we know that that distribution of this particular variable is very right skewed. And that's because of people like Mark Zuckerberg, Bill Gates, and heck, maybe some of you guys. So now we know why we look at measures of spread, the standard deviation, in addition to the averages. So stock A versus stock B. I want the spread in addition to the expected returns, or the average returns. Because if I know that the expected returns between the two stocks is the same, I'm going to invest in the one with the lower standard deviation. I'll be able to plan better. I get more bang for my buck. I take less risk per unit of return if I invest in stock B. So we know that looking at measures of dispersion are very important, and we can easily obtain these measures of dispersion from Microsoft Excel or Stata. Here's the measure of standard deviation for each one of these variables. And again, this data is highly skewed. If I go to the program and I import this data from a statistics module, I'm going to get Microsoft returns, daily Microsoft returns from an old stats module. So I'm running the program. Stata is still thinking. It's only because this data is pretty big that now I've got new data. So I can press browse like I did before, and now I've got one variable, daily returns for Microsoft stock. And this data is going to be much more normally distributed. I'll look at the histogram of the returns, and as you can tell, the average is about 0, which is not uncommon for daily returns. And the variability goes from about -1 or -0.1 or -10% to 10%. And we're normally distributed around 0 in this range. So again, we like to look at averages. If the data are skewed, we'll look at means and other measures of central tendency, maybe the mode. And we need to supplement our mean data and mode data with measures of dispersion, like standard deviation and variance. I can summarize the Microsoft daily return data. I can also use codebook. It's another command besides summary that gives me more information. So as you can see, I get the percentiles. I still get the average and standard deviation, but I get the range that we were referring to earlier. I can see whether or not any data is missing. I can see the number of unique values. And it looks like there are 5,000 observations in this particular data set. So all of that information is given. And again, I can construct the histogram. So let me go back to the stats review folder. I'm going to grab some more data. I'm going to run this program through grabbing this data, and I'll show you the log file before we start to hit our stats review a little bit harder. So view is another command, stat review.log. So this is the data that contains a log of every result that Stata produces. And again, we save these log files so that we can reproduce results. The Stata results window will fill up. When it fills up, the program will continue to run because we've set more off. And all of those results, once the Stata results window is full, all of those results past that won't be accessible. So we have to look at our logs. Or we can just run segments of our program by highlighting those lines of code and then pressing the execute option, which is this little file with a blue arrow on the bottom right. All right, so let's do a couple more definitions before moving on to some of the basics of probability. And we've mentioned these concepts very briefly, but let's be a little bit more specific. What is statistical inference? When you think of statistical inference, just think of learning something or using a few things to learn about all things. So the few things, that's the sample, all things, the population. So in statistical inference, it's basically the science of using sample data to make generalizations about an entire population, but this only matters if our sample is representative. So we want random samples. So each unit of analysis or each observation or each element needs to have the same probability of being selected. If that's the case, we've got a truly random sample. It's representative of the population, and because of that, we can do statistical inferential procedures. In other words, we can look at that sample and we can infer from it things about the population. Next, statistical estimation. So what is statistical estimation? When you think of statistical estimation, think of the science of using information contained in a sample to, one, find some sort of a statistical estimate of an unknown population parameter, and two, to place a bound on how far that estimate might deviate from an unknown population parameter. So again, the science of using information contained in a sample to find an estimate of an unknown population parameter and to place a bound on how far the estimate might deviate from an unknown population parameter. So essentially what we're going to do is use our sample information to find estimates for things like averages, maybe a slope coefficient in a regression model or an intercept coefficient. We're going to use the sample to solve for a statistic. And then we're going to use statistical ideas like the central limit theorem to be able to say something about how far that estimate deviates from the true population value. Again, we'll cross that bridge when we get there. But in statistical estimation, we're using the sample to estimate statistics. We look at how those statistics are distributed, just like we look at how variables are distributed. And then we use information from our sample and our understanding of how sampling distributions work to learn more about the population through statistical inference. Okay, moving right along to the next topic, probability. And this is something that you guys have probably learned at some point